Let's do a couple examples of Riemann sums. What's the Riemann sum for the function f of x equals 10 minus 2x on the interval from 1 to 3 for n equals 4? I guess that should be a question. So let's figure this out. We know that the Riemann sum is going to look like this. Okay, and this is the Riemann sum that uses the right endpoints. Right, these xi are the right endpoints on our subintervals that we use to build the height of the rectangles. So remembering that a Riemann sum looks like this, we need to fill in some of the unknowns. So the first one is n. Well, we're given n equals 4. Other things that we need to know was what is f? Well, we're given that here. So let's write that down. And then xi and delta x. Now let's do delta x first. Delta x, that's the length of our interval here, which is 3 minus 1, divided by the number of subintervals we have. So that's 3 minus 1 over 4. 3 minus 1 is 2, and so our delta x is going to be 1/2. And these xi's, these are the partition points. So they start, well, let's draw a picture over here. So here's a number line. We have our interval from 1 to 3. And the xi are the partition points when we partition this interval into 4 subintervals of equal width. So that's pretty equal. So I'll have it and then halve each half. So those are 4 subintervals. So the midpoint of the interval from 1 to 3 is 2, and then I can calculate exactly what the partition points are. So these will be our partition points for the Riemann sum, but this isn't quite the way I want to write it down. So the way I want to write it down is this. I want to use the idea that x sub I equals the leftmost endpoint plus I times delta x. This is the idea that if I wanted to get to the third partition point, I could start at the first and then add 3 delta x's. That's what this means. So for us, x naught is 1. I goes along with this, so we're not going to specify that because it's our index. And then delta x is 1/2. Yeah, so here's our formula for each of our partition points. And that's how I want to write it down for now. Okay? With all this information, we can just start filling this in. So our Riemann sum is the sum as I goes from 1 to 4 of f of xi. Well, let's do that. That's 10 minus 2xi times delta x. And I put a parentheses here just to keep the function expression together. So now I'm going to put in my expression here for xi. And then my parentheses again. And then I'll, instead of having that delta x, I'm going to put in the 1/2. So this here is my Riemann sum. I could stop here. But let's simplify this a little bit. We can multiply through by this minus 2. So we put 10 minus 2, and then when you multiply this minus 2 in there, this 2 cancels with that 2, so we get minus I. And all of that is times 1/2. And the 10 minus 2 simplifies to an 8. So I get 8 minus I times 1/2. And that's the simplest form of my Riemann sum. Again, I could have stopped here, and in fact, this is kind of nice because the pattern you see here really reflects the pattern in my function. And here's my xi. And looking at this way, and if you know what the xi is, you can read off just from this. If this is all I showed you, you could see, oh, my xi, they start at 1, they increase by 1/2. Right? So you could get a sense of what the interval is just from looking at this sum, whereas you can't see that here. Now at this point, this is where I want. This is the answer that I want. Now, how would you go about finding out what this approximate area is? Well, what I would just say is go to Wolfram Alpha, my favorite online computer, and type in this sum 1/2 of 8. 1/2 times, make sure you put that times in there, 1/2 times the quantity 8 minus I for I equal 1 to 4. Type that in, and Wolfram Alpha will understand what that means. In fact, it'll compute, or it'll show you this summation. It'll show you that this is how it interprets it, and then it will give you the number 11. So that's what you should get. There's a whole theory of summation notation that we're not going to talk about. Wolfram Alpha is here. We'll just let Wolfram Alpha do that work. Of course, you could write this out. There's only 4 terms. You could write this out and compute it by hand. You get 11. But if we have bigger and bigger, or more and more rectangles, it gets harder and harder to do it by hand. Wolfram Alpha doesn't care about that. Let's do another example. Let's write down the Riemann sum. For y equals f of x equals x squared plus 1 and minus 1 to 2 for n equals 9. So we'll have 9 rectangles, 9 subintervals of our interval from minus 1 to 2. So what does this Riemann sum look like? Well, let's build it. Let's start knowing that a Riemann sum looks like this. And let's figure out what we need to know. Well, sum from 1 to n will n the number of subintervals, the number of rectangles. That's 9. We're given that. We're also given that our function f of x is x squared plus 1. That's good. How about our delta x? Well, our delta x is 1 over 9, 1 over Rn, times the length of this interval, which is 2 minus 1. So that's 3 over 9, or 1/3. And then the xi. So what are the xi? Let's just do this. You don't have to do this every time. But we have an interval from minus 1 to 2. We want to divide it into 9 subintervals. So I'll divide it into thirds, and I'll divide each of those into thirds again. I think that's right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there's 9 subintervals. So I think this will be 0, and this would be 1. So this is a third, 2/3, 1 1/3, 1 2/3, minus a third, minus 2/3. Well, so these will be our actual concrete partition points, but that's not the way I want to think about them. I want to think about them in terms of, xi is the previous partition point plus the delta x. Right? That is xi minus 1 plus a third. But ultimately, the way we like this is we're going to start, say xi is the leftmost endpoint plus I times delta x. So in our case, that's minus 1 plus I times a third. That's what I want. And I think that's it. I think that's all we need. So let's do it. So I've got the sum as I goes from 1 to 9 of f of xi, so that's xi squared plus 1 times delta x. All right, so let's put in our formula for xi, right? We'll use this. So xi is minus 1 plus I times 1/3 squared plus 1. And delta x is a third. Okay, there's our formula for the approximate area using 9 rectangles. So here's our Riemann sum for n equals 9. Notice there's something really nice about this summation. There's some simplification that we could do, and we'll do that in a second. But there's something nice about this being not simplified in that you can look here at the thing squared. You can see that that's an expression for our xi. And so you can almost just look at this and say, yeah, here, this is like x squared plus 1. And then there's your delta x, which you can also see right here. And even just looking at the sum, if you know how many, you can see I've got 9 subintervals, each of with 1/3, so that means my interval is of length 3. The left endpoint is -1. So just looking at the sum, you know that you're doing a Riemann sum from -1 to 2. Interval of length 3, starting with -1 at the left. Let's simplify this out a little bit. So we'll square this. When we square this, we get 1 minus 2 times I times 1/3 plus I squared times 1/3 squared. And we can simplify this by combining this 1 and that 1. You get 2 minus 2/3 I plus 1/9 I squared times 1/3. And, that's as simple as we can go. Can't combine any more terms. Each of these terms is distinguished by having a different power of our index. Here's our index to the 0th power, index to the 1st power, index to the 2nd power. If we want to figure out what this value is, like I did in the previous example, we're just going to throw this into Wolfram alpha. So for this, I would type sum 2 minus 2 divided by 3 times I plus 1 divided by 3 squared times I squared. And I put that in parentheses, and I put a times 1/3 for I equals 1 to 9. That's something Wolfram alpha is going to understand, and it's going to give you the number 104/9, which is approximately 11.5 repeating. And that's the approximate area under the curve. And just so we're all on the same page about this, what did we just do? Well, we looked at the parabola, and we approximated the area under that curve using rectangles. And there are rectangles that This is a very rough sketch. I just made a mistake on one of those rectangles. But that's what we get. And yes, the picture shows that this is an approximate area. It's not the exact area. And you can see the error here is where the rectangles overlap above our region. So there's some overestimate happening here. But over on the other side here, there's some underestimate happening. My rectangles are below the curve. But that's okay. We know it's an approximation. That's all we were trying to do, is get the approximation. And the cool thing about this process is there's nothing special about this 9. I could have made this into 90. And this summation becomes very similar. This expression changes slightly. And then we can throw it in Wolfram alpha and get a number. But I'm getting ahead of myself. This concludes this example. This concludes the screencast. And the next screencast will be on the definite integral. See you then.